Hello everyone, and welcome to another sound design lecture where we will be introducing the audio worklet of the Web Audio API. And here are some pretty advanced concepts, but I'll try to show it in the simplest, most straightforward way, working from, one of the basic, but also one of the most essential audio worklets, and then adding in a bit more functionality. So here we go. Now, in the Web Audio API, it features a lot of useful built-in audio nodes. Depending on how you count it, about 18, maybe 20 of them. But the default ones are not enough. Not enough if you want to do lots of interesting and diverse things with audio. And sooner or later, you will run into problems if you only restrict yourself to the built-in nodes and what can be done with them. So, for example, there's no noise source. There's ways that you can create noise, but there's no source node like the other source nodes that just automatically continually generates an endless stream of random numbers as an audio signal. And some of the filters that are designed are rather strange ones. They're not the choices that one might usually make. So we haven't really talked about filters yet in these lectures, but there's basic filters to, for instance, remove all of the high frequencies in a signal that are used in different programming languages. And the way in which they are designed in the Web Audio API are not the same way they are in other languages. Or other development environments. What that means is that many of the objects, the functions and methods that one might make in other development environments for working with audio, like Max MSP, Pure Data, or C-Sound, they don't have an audio node that's equivalent to that. Also, there's sooner or later any other audio processing you can think of may or may not be there within the default nodes. So though you can do a tremendous amount with them, you really want more functionality. As is the case with almost any rich audio environment, you want ways to extend that environment. The audio worklets are the way to do that. They are the format for designing your own audio nodes. And it's pretty powerful. If you're familiar with VST programming, it's like the processor routine. Basically, within that routine, you can do any fancy manipulation of audio, and it's the core of a VST plugin. There's similar things with audio units, similar things with other audio formats. Now, a little bit of history. When the Web Audio API was first designed, it didn't have audio worklets. The closest it had was a JavaScript routine called the script processor, but it ran on a different thread than the Web Audio API, which meant essentially you stopped the Web Audio API to do things with the script processor, and it didn't work in quite the same way. What the audio worklets allow you to do is to have audio nodes that work and operate and are treated in almost every sense just like the built-in standard audio nodes. So let's give an example. We're going to look at a noise generator. It's perhaps the first thing I noticed that felt like it was missing from the Web Audio API as soon as one starts working with it. So we have constant source nodes. We have oscillator nodes. Those are both scheduled sources. Within the oscillator node, there's some standard or default types, like the sine wave, the sawtooth, and the triangle. But what we don't have is an audio node that spits out noise, white noise. So random numbers, uniformly distributed, every single audio sample. And what we want with a noise generator is to create a node that outputs audio where every sample is just a random number between -1 and +1. Then we can filter and shape that to create what's known as pink noise, sounds more natural to the human ear. Or we can use that as a little noise on top of anything else. We can use it to degrade a signal when we want to. We can use it to shape a sound. Start off with noise, filter it, apply amplitude envelopes, and get something sounding like noisy sound textures, like the sound of rain or the sound of wind, for instance. So we can do a tremendous amount with a noise generator. It's used in sound synthesis, used to create various audio effects, and also sometimes used in analysis. Let's begin. So a little bit about the audio worklet. The audio worklet, think of it as creating an audio node from the ground up. So you can define the parameters, you can define default values for each of those parameters, just like we have a gain parameter for the gain node, frequency parameters, and other parameters for an oscillator node. It can have any number of inputs and of input channels, of input signals and output signals. So there are a few nodes that have multiple input signals, multiple output signals, which we haven't talked about yet. You can have a node used for mixing, or takes two different signals or tracks and makes one the left channel, one the right channel. Each of those input or output signals can be multi-channel. So you can do some really wonderful things here, things that are not done in any of the built-in nodes, where you have, say, guitar, bass, drums, and vocals. Each has stereo tracks coming in, and it repositions all of those stereo tracks. By default, it processes 128 samples of audio at a time. And every time it always deals with 128 samples. This is slightly different from things like the VST format, which might allow you to have your own choice of how many samples of audio it works with at a time. But 128 samples at a time is a very low number, and using some programming with circular buffers and delay lines that we'll talk about in a later lecture, you can treat it as if it's processing many more samples at a time. 128 samples means that with a typical sample rate of, say, 48 kilohertz, the most common one is actually slightly less than that, 44.1 kilohertz. But with 48 kilohertz, I believe that equates to sampling or to dealing with a frame of 2 2/3 milliseconds. That's very short. Okay, so now let's give our simple noise generator. Here's the shortest way I can think of to write it. Starts off with this line, register processor, which basically is giving a name to the audio worklet. Then there's a call to the constructor, which has defined super. Now, it says in the specification that this is required. I don't think it's actually required in all cases. If you're not doing anything with the constructor, then you can leave this out entirely. Then we have the process routine within the processor. That's the important one. So it's where we deal with the inputs, but in this case, it's just a generator, just a source. So we don't have any inputs, and we deal with the outputs. We define an output here to be an output channel. So of all of the outputs, just the very first one, outputs of 0, and the very first, so that's the first signal or track, and then we have the very first channel. So our output is just going to be that signal number and that channel number. And then for every sample in that output length, which should be of length 128 samples, we define that the output is 2 times the built-in or the JavaScript routine math.random, -1. Now math.random generates a number between 0 and 1. So if we want a number between -1 and 1, essentially the range of audio samples, then we take that random number between 0 and 1, we multiply it by 2, so now it's between 0 and 2, and we subtract 1 from it, so now from 0 to 2 it becomes -1 to +1. And that's it for the whole of the routine. The last line here, return true, is a requirement in order to keep the processor alive, to keep it still generating output. If you ever set this to false, then, which might be a condition of what are the computed values, then the processor is no longer alive and it essentially stops. So let's have I wanted to show you a little bit more. So that's the audio worklet defined there. Now, the audio worklet processor definition, which we gave here, must be declared in a separate source file from the main JavaScript file or HTML with embedded JavaScript that you are working with. It's a security reason. It prevents nesting things in problematic ways that can essentially crash the browser. So we have a different file, the main JavaScript file, and in the example I give, we'll have that JavaScript embedded into the HTML, where we specify a new context, just as always, but then we load in our worklets with what's known as a promise statement. And that occurs here as one of the methods with the audio context. We have audio worklet where we can add a module, and we've defined we've saved a file where this is, which is called worklets.js. So we have audio worklet, add module, worklets.js. Then, if the promise returns true, essentially if there wasn't a problem in finding this worklet, then we can run the following. So that line just discussed loads and registers the audio worklet. Then what we choose to do is we create a new audio worklet node, similar to creating an oscillator node, but now we need to define which processor in the file of processors that we just created here, which processor we're going to use for that node. Now, we could only have one processor here. We could even have several of these add modules from different files and things, but in this case we have one file, one processor there, and we create a new worklet. Now we can work with that worklet just like any other. We can connect it, we can disconnect it, we can create multiple copies of the worklet, we can connect it to different things in different ways, very similar to what we've done. In this case, our worklet does not take any inputs, or at least does not do anything with any inputs that are connected to it. And all it does is output one channel of noise. So now let's hear what that does. So I'll make this a little larger for you. You can see I've already tweaked the code a bit here. I've taken out that first bit of code where we define the constructor, because we don't need it. We're not initializing anything in this worklet. I also, rather than defining the number of tracks or signals, the number and the channels, I've just said for the first track, first channel of that track, and for all the samples, this is 128, but we defined it .length just in case the standard does change and allow us to have variable lengths within an audio worklet. And then that output is like this, just as before, generating random numbers between -1 and +1. And then we have one HTML file here with the JavaScript as mentioned. We add a module with the noise worklet. We create our worklet node. We connect that node to the destination. So let's go. Here it is. Should be the sound of noise. So that's it. That is basically just about the simplest, very, very useful audio worklet I can think of. And it might seem complicated at first, and certainly other examples given in other places can be incredibly complicated, but ultimately this worklet is just 6 lines of code, and really only 4 lines that actually say anything meaningful. Okay, so let's move on, because we now have a working worklet, but we can't do anything really interesting with it. If you notice this worklet, it takes no parameters, so it just generates noise. Now, you can still do a lot with it because you can have it connect to a gain, so you can have a changing level associated with the noise source. But there's plenty of others where you might want adjustable parameters, or you might need to store variable values and do more complicated processing within the worklet. So we'll introduce one more right here to do a little bit more, and this also turns out to be quite useful. I mentioned that some of the filters within the Web Audio API are unusual ones. Now, you don't need to know much about the filters just to understand this example, or even about filtering. But the idea is that by performing a simple mathematical operation on a signal, like taking every sample or every 2 samples and taking the average of them, you change the frequency content. So if you have a signal that is changing very, very rapidly, and you average the values of that signal, then it changes much more slowly. You're removing the high frequency content from that signal, and it will change the sound of that signal. One way to filter a signal is what's known as the exponential moving average filter, or the smoothing filter. And it's done like this. If your input samples, every sample period, are x of n, so x of 0, x of 1, x of 2, then the output after filtering is some constant c times x of n plus 1 minus c times the previous output value, y of n minus 1. So you're basically smoothing what the output would be. The output is a smooth version of the input signal. So if the input signal jumps from a value of 0 to a value of 1, then the output will slowly approach that value of 1, but never quite reach there. It's a very similar function to what we saw with automation curves for an exponential ramp to a particular value. So, or the exponentially moving towards a value. So how are we going to do this? We'll change it very slightly from what we saw previously, because we want to take a filter from a different development environment and re-implement that in the Web Audio API. So Pure Data, graphical programming language for working with audio, it has its object LOP, standing for a low-pass filter. And that low-pass filter implements this equation right here, but C is defined as 2 times pi times some cutoff frequency for the filter. So here we're going to have a parameter for our audio worklet. We want to adjust the frequency. So we have a static get for the parameter descriptors, where we can define all of the parameters we work with and their default values or their ranges, like the minimum and maximum value. And here we just have one parameter, we call it frequency. I'm not bothering to specify its minimum value, its maximum value, or anything else about it, just the default value of 100, meaning 100 hertz cutoff. We're going to try to remove frequencies beyond 100 hertz in this filter. Now here we have a constructor where we're defining a few attributes of this audio worklet. So internal attributes that we're going to work with. And we work with this, what we're calling last out, which we set to 0. And we do that because we have the current output is a function of the current input plus a previous output. So we need to define what it's going to be when it's the very first time we compute it. And that's this. Very first time we compute the current output, we say that the last output was 0. Okay, so we have the input track or signal is going to be the very first one. The output track or signal is the very first of that outputs. So we're assuming here that we will just work with a single track. And let's see. Yeah. Get parameters descriptors is where we defined the audio parameters. We gave it a default value, but we can also define minimum value and maximum value, and the automation rate, but we haven't discussed that yet. And last out is going to be global to everything else. So process will be able to see the last out because it was defined in the constructor. And here we go. We say for the channel, which is okay, so I'll clarify. We specify that there's one input track or input signal. We specify that there's one output track or output signal. But how many channels? You could have stereo input, so it will default to stereo output unless we say otherwise. So now we're saying for each of those 2 channels in stereo, if it's stereo, or 1 channel, if it's mono, we're going to look at all of the samples within that channel. So for a given channel, we then specify, we give that channel a name, input channel and output channel. And now what we do is this line here, because we're matching pure data's low pass filter, where the low pass filter defines the coefficient. I'll go back. The coefficient is the C value right here. It's the one parameter we're working with, but here it's defined in terms of a frequency as 2 times pi times some frequency parameter that the user controls divided by the sample rate. What it means is that roughly this frequency is where the signal transitions from leaving the content roughly unaffected to filtering the content at a higher frequency than that value. So it's like a cutoff value. And then we say for every sample within those 128 samples in a channel, the output equals the input times the coefficient plus 1 minus the coefficient times the last output. That's the equation we worked with before. And then last output equals what we give to the output channel. Now, this code here is rather simplistic. You should actually be more careful about how one deals with the channels, but it's good enough for us to work with right now. And this last line allows us to keep track of the previous output every time. This last line, by the way, we really should make last out an array so that there's a different value of last out for every channel. But it works perfectly fine if there's just one channel we're dealing with. Okay, so now let's look at using this low pass filter. And here we're going to actually use both the worklets we've created, the noise one and the filter worklet. So we'll generate the noise and then we will filter that noise. And in what's shown here, I use one line to change the filter's frequency from the default value, which I gave as 100, to a new value of 50 or 50 hertz. So I'm really trying to filter out most of the high frequency or even mid-range frequency content and just keep very low frequencies. How does that work? Well, same as before, we add module. We have one file to add modules from here. I could have made an array of different files, but here there's just one. And I create two different worklets, worklet nodes, one called my noise, the other called my filter. Then here I use get, and I specify the frequency parameter. So it's actually my filter. From the parameters, get frequency, specify what that's going to be at 50 hertz. And then I connect the noise to the filter, connect the filter to the destination. Okay, so let's look at an example. And I've changed the code here slightly as well. Not making it simpler, but adding in probably a bit more functionality. So here's the filter, and I'm going to have a user control here where someone can specify the filter value. So it's a range or a slider control. And I'm going to show what that frequency is that we're associating with it. Generate noise, filter that noise dependent on the range or slider control's value. So they're continually moving that filter around. And then the audio worklet, notice I have two here. I have the noise generator from before and the low pass filter, which was just described. And this low pass filter is, I think, exactly the one that was shown in the slides. So here we go. Go over to the filter, and I have lots of different examples of worklets here. So I'll leave it for a second because the way it works when I'm showing it off locally, it automatically starts, and I didn't put any stop in there. So I'm going to move the slider around. Hopefully you'll hear it okay. When I move it to the left, I'm trying to remove all the frequency content except the very lowest frequencies. When I move it to the right, I'm keeping almost all of it. And you should hear the sound change. And it's not a perfect filter. There's a lot that's a lot of frequency content that's still kept of high frequencies, but you can see how it works. So what did you learn here? You learned how to create a worklet, how to deal with the fact that it can have different numbers of sources of channels. In most cases, with most of what we do, you'll only be interested in one source for the input and the output that has just one channel, when you're not working with stereo or surround sound or anything like that. And learned how to change parameters and define those parameters and work with the parameters and also to have some internal parameters that are stored and changed or updated from 128 sample blocks to the next 128 sample block. Okay, so that concludes this short lecture about audio worklets. As always, if you have any questions, please contact me and let me know. And thanks very much.